So let me start this session. Okay, so I would be handling the control part of this course of robotics technology. So until now, you would have learnt about the kinematics and the dynamics of robot, and probably you would have concentrated more on the robotic manipulator part rather than mobile robots part of it. Okay, and so my lectures would also concentrate on the control part of robotic manipulators, and if time permits, and if you are also interested, probably we can touch in the uh, on mobile robots also. But let's see that how things proceed, because the amount of mathematics that is required would also vary with the amount of exposure that you have. Okay, let me start the session. So what I plan to do in the next, say, 8 or 9 lectures would be, first, so in this lecture I would go over, I would review the few basic concepts that would be necessary to understand the further lectures. So that would I would go about the concepts of what is a state space, what is a transfer function, and more importantly, what is the time response, what is meant by time response, and analyze the time response in a few simple cases and try to relate to what would it translates to the requirements that we have when we are trying to control a robotic manipulator. Okay, then the subsequent lectures would concentrate on different techniques by which we can implement the control. So we would go through, initially we would go through the most simplest types of controls that are used, that is the PD and PID controls. Then we will go into the concept of state space or state-based control, where we will see control techniques like feed forward and computer torque control. That is what CTC is. Okay, so this, initially we would go joint by joint. So we will design independent controllers for different joints of the robotic manipulator. Then we will try to design a control for all joints together, that is a multivariable control. Okay, and we will again explore the possibilities of using PD or the simpler PD or PID for the multivariable case. And we will also explore a technique called as inverse dynamics based control. Okay, and finally, in the final part of this module, we would try to see what would happen, or what are the constraints that are imposed when you have some constraints in the motion of a robot. Say, for example, let us say that you have a robotic manipulator. So there is one thing, that you have a robotic manipulator and you want the end effector to reach certain position. So that is you can have some techniques by which you can make this, you can actuate the different joints, and the end effector can reach whatever desired position it is. So that we'll be exploring in these two parts. However, let us say that your robot is it's a sort of an articulated hand, and now you want to, let us say, grip an object or twist open a cap. Okay, now it is not just moving through the environment, it is interacting with the environment also. So there will be certain forces. So if I'm grabbing using the gripper, if I'm grabbing an object, then the gripper cannot move in certain directions. So there will be certain velocity, and there will be certain force constraints that happens when your robotic manipulator is not just moving, but it is interacting. Okay, when it is interacting with with the surroundings, with other objects in the surroundings, then you would have certain constraints. We will briefly see how those constraints can be mathematically put, and let us see that how much further we can go into that direction. Meet of today. So what we have here is that whenever you're talking about control, in this, at least in the robotics context, here is that you have a robot and to apply forces or torques. Okay, let us say if you have a revolute joint, you are able to apply torque to the joint through some actuator, and if you have a prismatic joint, you are applying a force, and that force is acting on the joint and making the joint move. Okay, so basically what you have is a force or a torque that is applied to an object, and you are basically interested in the position of that object, and in a sense also you don't want the object to move too fast or too slow due to certain other specifications that you have, certain other conditions or constraints that you may have. So you want the object to move from position A to position B, while the velocity should follow certain constraints. Probably the acceleration should also follow some constraints. Okay, so these are the specifications that you have. You would have seen this figure of the free body diagram for a mass that is connected by a spring or the force is applied to it, and the dynamic model, the force to position model of that is quite a simple second order differential equation. Okay, and coincidentally, if you make the dynamical model for a for a manipulator, here you have a 3-link manipulator. Here too, you see that the structure of the model is quite the same. So instead of the force here, you have a torque here. Instead of the spring constant K or the restoring force Kx, you have the gravity terms G of Q. Instead of the damping coefficient, you have the Coriolis and the centrifugal forces acting. Okay, and instead of the inertia or mass here, you have the inertia matrix here. So in a sense it is simpler, and in a sense it is quite different also, because here you have M, B and K being constant. Here it is not so. These are values that change with Q, they change with time, they change with Q, and here you have a single position. Here Q is actually theta 1, theta 2, theta 3. It is a multivariable thing. So the problem, even though it looks on a surface, these two systems look very similar, and it seems that there is some similarity. There is something that I can work for this system and apply so that it can be applied to this system. There are quite a few roadblocks to actually implement it. Okay, let's try to backtrack it and try to make the system, represent the system into something that is similar to the first one. Okay, and and if there are approximations to be made in the way, let it be, and let's again unravel the approximations as we proceed further. Okay, that was one thing. Second point is that we had seen here that you want the object to go from some position to some position. Okay, and of course when it is going from some, and when it has some velocity constraints, what you are actually doing is the path planning. Okay, so here what we again want to see is that in which coordinates should I do the path planning, because I can say that I am doing the path planning in the workspace, okay, or in the joint space. Okay, because if I can say that I want X, Y, Z to follow certain coordinates of the end effector, or I can say that theta 1, theta 2, theta 3 should follow certain trajectory. Okay, in theta 1, theta 2, theta 3 coordinate. This is very intuitive to do because I can see what the trajectory is. Theta 1, theta 2, theta 3 has to be derived. So I have to use the inverse kinematics to go from XYZ to theta 1 coordinates. However, the torques are being applied at these joint locations. So it is easier to design your control, your tau, if the transformation, if the control is being designed for in terms of theta 1, theta 2, theta 3. So further in the lectures, we will be actually dealing with designing tau, given that you have trajectories for theta 1, theta 2 and theta 3 rather than for xyz. So we will be doing our design in the joint space and not in the task space. And let's come back to task space when we are say confident enough to get to that location. So the objective is to design the control input, which when applied to the manipulator or to the system is to, and so that the motion or the variation of x, as in the linear case, as in the case of that mass of a block, or in case of a manipulator, the positions. Okay, I want to control q, the position q, and I want to design a torque tau so that the position q is controlled. Okay. However, to do this, I need a better understanding of how the torque will affect the position. So I do have the dynamical model. So given a torque signal, I can find out what will be the actual position of the q, what will be the actual theta 1, or what will be the joint angles. However, I can't characterize it unless I know how to characterize it, unless I know that whether I am applying the right tau, and I can predict whether the force or the torque applied is going to lead the model, is going to lead the manipulator in the right direction. I can't actually design the torque. So I should know how the torque is affecting, and I should not be able to, I should be able to characterize the system. Okay, so merely knowing how to uniquely determine the position is not enough. I should be able to qualify whether the torque applied is leading the system in the correct direction. Okay, but to know that, what I want is, I want to be able to write the expression for q of t in as clear terms as possible. Okay, but seeing the even this structure, it seems that this is very tough, because it's a system, it's a second order differential equation, a nonlinear second order differential equation, a nonlinear second order differential equation in n variables, and there is interaction between those variables. So what you have here is in the mass matrix, you would have product of the coordinates of the positions, and in this Coriolis matrix, you may have qi qj term coming up. So qa dot qj dot term coming up. So you have so much of nonlinear interaction that it becomes very, very difficult to discern, to even try to solve this directly. So some simplification is needed. Okay. So first, let us say that let's sort of forget treating this as one equation. Let us try to set of n different equations where I take each of the equations separately. So I take each of the rows in this equation as a different rows in this equation with n variables as into one equation at a time. So the problem is now slightly simpler, since there is only one signal that I'm going to design, tau, rather than all the n tau n torques simultaneously. However, this is still a problematic thing, because the problem is still nonlinear. So I still have that qi dot the qi dot and qj dot multiplication, and still this equation that I have is going to be nonlinear. Okay, let me actually put this in a pointer. Okay, so this has become a single variable. However, this side is still not resolved. It is still nonlinear. So let's take an example here. So here you have a simple pendulum. Okay, there is a single equation, there is a single theta. However, the equation describing the single pendulum is still non-linear. You have the sine theta term. So with this sine theta, I'm not really sure that what will be the equation that will, what will be the equation that will, what will be the equation for theta of t. Okay, but on the other hand, let's take this mass damper system. We can easily see that if you have this system and if you say that it starts with some initial condition x at 0 is x0 and the velocity at 0 is v0, I can actually write x of t. Okay, of course, when there is no external force being applied, I can actually get an expression of x of t. So if I'm able to get this equation to this format, then it seems that there is some solution that can be found out or some simplification that can be done. Fortunately, the first step now is that let me consider what is the behavior of theta very near to theta equal to 0. Okay, so near theta equal to 0, that is when theta is approximately 0. Okay, you have sine theta being equal to theta. So I can have g sine theta being approximated to g theta and get an equation that is simpler. So get a differential equation that is simpler. So this is called, this process is called linearization. So, and the method to simplify the model subject to the variables being close to some known reference location or known reference point is called as linearization. So we would be, the first step that we are doing is to linearize the model. Okay, but the linearization is going to happen, is going to be useful when we are doing it around some reference points and some properties of the reference point is to be known. So one of the most chosen or most favorable type of reference point are equilibrium points. So these equilibrium points are the points at which the system is stationary when it is left undisturbed. So you might have known about, you might have been familiar with the concept of equilibrium. So equilibrium points could be stable, unstable, or neutral, like in this case. So when there is no external force applied, all of these three objects would be stationary at their own at that position. However, the cone being standing on its base will actually be stable, will remain, will come back to that base if you give some perturbation. This, the sphere is, will, if given some perturbation in this direction, will shift to a new equilibrium point and stay there, while the inverted cone is going to just fall down. It will go away from the equilibrium point. Okay, and probably attain some other equilibrium point. Okay, so and that, so it is an unstable equilibrium. So this is not robust against perturbation. This will actually shift to a new equilibrium point. This is robust against perturbation. Okay, what is to be noted is that mathematically, if you have an equilibrium point x, then x dot x equal to x0 is an equilibrium point. Then x dot is 0. Okay, when at x equal to x0, and x double dot, or all the higher order derivatives will be 0 at the equilibrium point. Okay. So that is the mathematical understanding or the tip that we have to keep in mind. Okay. Now let us say that we have an equilibrium point in the case of the manipulator. We have an equilibrium point q0, and that equilibrium point is maintained by application of a torque tau 0. Okay, and as we have seen that for this to be an equilibrium point, q dot at q equal to q0 should be 0, and this second derivative, the acceleration, should also be 0. Okay, and if you substitute this, you would see that you will get that g of q0 is tau 0 at the equilibrium point. Okay. However, we are not actually interested at the behavior of about the behavior at the equilibrium point. We want the behavior around this equilibrium point. Okay. So what would happen when Q is Q0 plus some small delta Q? What is happening there? Okay. So if you make the perturbation, then you get a model that looks like this. Okay. This can actually be decoupled or written collecting d of q0 on one side and all the rest of the terms as delta d, and similarly for the Coriolis matrix and the gravitation factor. Okay. And now what we are interested is to relate this delta q and this delta tau. Okay. We want to relate delta q and delta tau. So, and if you are ignoring terms of the type delta d times delta q double dot or delta c times delta q dot, so these small perturbations, if you ignore it, what you end up with is a model that has this particular structure. Okay. Now, if you see this model, yes.
So how did you linearly distribute like d of q naught plus delta q? You wrote at d of q naught plus delta d.
Yeah.
How can we linearly write that?
No, see d of q naught
D
plus
is a
delta q,
function.
okay,
Yeah.
is a function, okay, that involves q naught plus and delta q. Okay.
Right.
Let me say that delta d is equal to d of q naught plus delta q minus d of q naught.
Okay. Okay.
Okay. I don't really care. I don't really care what is the actual expression of delta d. Okay. What I say is that what I assume is that when the delta q is really, really small, delta d is also a small quantity. Okay. Small enough that if I multiply, I can ignore. What I'm saying is that delta d is small, delta q double dot is small. Okay. So their product I can ignore, but the product of delta d, so yeah, the product that I can ignore, I am not ignoring this term. Okay. And I am not ignoring this term. Okay. So what I have here is, yes. So let's actually, this seems to be a little confusing. Okay. So let's analyze this one equation. Okay. Let's analyze this one equation. So from this product, you will get four terms. So delta d into delta q double dot is being ignored because we say that both of them are really small quantities. Okay. Delta means q0 double dot. What will that be? Q0 double dot should be 0 because it's an equilibrium point. Okay. So out of the four terms that I get from this product, okay, only one of those terms will remain, that is d of q0 into delta q double dot. Similarly, in this two, you have only one term, that is this one into delta q dot being remaining. Okay. And of course, g of q0 was tau 0. So they get cancelled out. Okay. And you'll get this equation. Now, in the final equation, which relates delta t and delta q, you're in luck because this is a constant, this is a constant, and this is also a constant because q0 was fixed. So you have been able to get a nonlinear equation, approximate it, and get a linear equation by just making the assumption that I am perturbing this nonlinear equation, the point at which I'm studying this nonlinear equation, to be very close to a known point. Okay. At a known point, that's an equilibrium point, and at the equilibrium point, the velocity and accelerations are 0. In fact, even if they are not 0, you can actually make it, it doesn't really matter because those things will get cancelled out eventually. But for now, let us consider the equilibrium points alone. Okay, so if the takeaway is that if I am going to find the perturbation, how the perturbations interact near an equilibrium point, we come to the conclusion that it is modeled by a equation, by a differential equation that may be of whichever order, but that is going to be linear. So the point is, it is linear equation. Okay. The other point that you have here is that if you see any of these equations, the factor of time is not coming at all. So you don't have you don't have any of these parameters like the length of the manipulator or the mass of the manipulator changing with time. So the other point that you have is something that is called as time invariance. So these are time invariant also. So the dynamics are not changing with respect to time. You do have certain specific systems that are not time invariant. But let's not go into that, because why mess up our head with those details. So what we are talking about is linear is systems, and they are time invariant systems. Okay. Now there is another. So this is so you can represent the perturbation as a linear time invariant system. Okay. On the other hand, you can also do this thing. You can say that you can use the concept of state space to represent the behavior. And when you say state space, what you want is you are trying to choose or find different variables whose behavior actually determines the entire behavior of your robotic manipulator. Okay. Now, let us say if I have a robotic manipulator and it has the joint positions as q1 to qn and the joint velocity as say v1 to vn. Okay. And if I already know the different lengths, okay, of the robotic manipulator and the geometry of the robotic manipulator, the masses of different parts of the manipulator, okay, these are not variables, these are parameters. So these are parameters, okay, which we assume are not changing with time, and these are the variables that we are assuming that we need. So other than these variables, do you need anything else to actually determine how the manipulator would behave? Okay, let us say that in addition to this, if I give the torque, if I give some torque to the manipulator, let us say this, let's pose this question in this manner. Let's say that I am giving some torque to the manipulator, okay, and I ask the question that what is the position after I apply this torque? Okay, so the immediate thing is that okay, the torque is applied on the torque is affecting the acceleration of your link. So the acceleration will it will affect the position. Okay, so you will have, if I apply a constant torque, I will have something like this. I'll have some sort of an acceleration. Okay, so the position with respect to time, okay, will look like a parabola. So this is a very simplistic case. Okay, will look like a parabola, but this point, okay, actually depends on two factors, because I have to know what is the initial position and the slope, whether it goes in this manner, okay, or so, will depend upon the velocity. So I need both the initial position and initial velocity, okay, for knowing the final position of my manipulator. Okay, so and I don't require anything else. So the minimum set of variables that are required to actually describe a system, any system in general, is called as the state of the system. And the way to mathematically represent a system using this are to write the differential equations for each of these variables. So what I want is, if I say that q1 to qn and v1 to vn are my state variables, I want to find equations for q dot, q1 dot, q2 dot, and so on, and similarly v1 dot or v2 dot. So if you have a single link as we have here, so we will have q1 dot is of course v, the derivative of time derivative of the position is of course velocity, and v dot in this case is a function that is dependent on my torque, okay, and q and v. Okay, and you see that there are no other variables that are required to describe this state equation, though there will be some parameters uh, are dependent on the length and mass of the manipulators that actually come somewhere in this D and in this C, and of course in this G also probably. Okay, but those are parameters, those are not the variables. The number of variables that are required in this case is just two, which is just the position and the velocity. Okay, that is as far the state space is concerned. Okay, and you can do the linearization in by seeing the state space also. Okay, so as you said that as I said in the linearization part, you go for this delta x. So what we want is delta x dot. So x dot equal to f of x is being written. If I write in this case, if I say x is this q and v, this entire equation can be written as x dot is some function of this x. Okay, and there is of course there is a tau also here. Okay, and we want to write delta x dot. Okay, delta x dot is actually the Jacobian dou f by dou x evaluated is at x equal to x0 times delta x. And now this Jacobian, since it's evaluated at a constant point, will again give a constant matrix. So you'll again end up with a differential equation, of course a matrix differential equation, and this approach of design is again called as state space approach. We may come back to this, okay, but for now let's see that this is another way to linearize the system. This is another way to analyze it. One way is to deal them in the get the differential equation, get a linear time invariant model, and proceed in a different direction. Other way is to get the linear time invariant model in state space by separating out the velocity as a different state, q as a different state, and or use q or q dot and operate on q and don't recognize and say that this is the derivative of q. I don't say this is a velocity, I say this is a derivative of q. Okay, let's this terminology that I'm using right now may not be very clear, but if you go further, you may sort of be able to differentiate in those two terms. Now what we'll first look into is the transfer function approach. So for the P and PD design, what we actually will try to look into is the transfer function approach. Now what is a transfer function? So you are in your manipulator, you are giving a torque in, something happens here and you get the position q outside. Okay, and you now got a differential equation of the type d q double dot plus cq plus some k times cq dot plus kq is equal to tau. So you have an equation of this type. Okay, now if I have the Laplace transform of these two equations, if I have a Laplace transform for the input torque tau and the output signal, the position signal q, the ratio of their Laplace transform, assuming zero initial condition, is called as the transfer function of this system. Okay, now in the case of the linearized manipulator, this will be delta q by delta t, which we may represent, which we may write as the ratio of two polynomials c of s and r of s. Oh, not sorry, no, which you generally write it as. So if you say this Laplace transform of this is C of S, and for this is R of S. Okay, what you have is C of S by R of S. Okay. In general, a Laplace transform, the most general Laplace transform, can be written in this manner, where it is a summation of first order of terms where the denominator is a first order polynomial in S, and another set where the denominator is a second order polynomial in S. Of course, I assume that you know the Laplace variable S and how the Laplace transform is obtained given a signal. Okay, so the transfer function generally has this structure. So let us go and try to uh, get a hold of this thing. Okay. So when you have a Laplace transform, if I write it in a more general manner, allow the uh, then you have a ratio of two polynomials. Now this polynomial would have some roots. Let's say that those roots are z1 to zk, and the denominator polynomial also would have some roots. Let us say they are p1 to pk. These p are called as the poles of the system. Okay, and these z are called as zeros of the system. Understanding what z is quite trivial. Why they are called as zeros of the system is quite trivial, because if you try to evaluate g of s at s is equal to some zi, you will get the answer as 0. So that's why they are called as zeros of the system. Okay, and if you try to compute what is the value of the polynomial g of s, okay, as s tends to pi, and if you try to plot it, you will get a plot whose magnitude just goes off the near p equal to p0. So it's as if there is a tent pole that is being installed at this particular location. So that is why these positions, these points are called as poles of the system. K is called as a gain. I don't think I would need to explain what you mean by gain of the system. Okay, and the number of poles that you have, or the order of this denominator polynomial, is actually called as the order of the system. Okay, and for all practical purposes, for all practical systems, the number of zeros and the number of poles are related, that the number of zeros, the small k, is actually always less than the number of poles. So k is always less than n. That is something that you will always encounter in practical systems. And the reason for that is that whenever you are doing this, you are handling systems that have inertia in it. There is no physical system that doesn't have mass at all. Okay? There is no electrical system that doesn't have any induction at all. Okay, so even if you take a wire, there is some sort of there is a minimal some sort of inductance in that wire. There is some sort of capacitance between two wires. So that will cause an effect that will act like a mass, that will act like a dampener, and that will create an effect which in turn would always mean that the number of zeros in a system is always less than the number of poles in the system. Okay, so that is something that you would need to mind. You can you need to keep in mind. Okay, while designing, so this will become very important while you are designing controllers. Okay, let's say where you want the poles of the system to stay. Okay, so what comes out is the initial concept that comes before I try to extract any performance out of the system. The first concept that has to be understood is stability. I don't want my manipulator joints to just swing wildly. I want the manipulator joints to move in a smooth manner, move in a very regulated and in a manner that is acceptable. So what I need is the error slowly tends to 0. So if I am trying to plot error, the error should slowly tend to 0. Error should not blow away. Okay, this is definitely it's very obvious to see that I don't want my error to blow away. I want the trajectory to be followed rather than the manipulator going in a totally opposite direction. So the important point is what you call as stability. Okay. So if you see this, the poles and zeros, if you track the pole and zero location, in general, what you want, the poles and zero location can be in general for any system, for any transfer function that you have, the poles and zeros can be anywhere in the S-plane. However, if you try to write the transfer function and find the inverse Laplace transform of it, okay, you would find that whenever the real part of the pole is greater than zero, whenever say sigma I is greater than zero, you have a signal like this. So it will have e raised to sigma into say something like sine of omega t. Okay. Now e raised to sigma t is a signal. If sigma raised to sigma t is a signal that is exponentially growing. Okay. So I don't want that. So what I would require is that I don't want the poles to be in this location. Okay. I don't want sigma should be greater than zero, at least for the poles. Zeros with sigma greater than zero are acceptable, but poles with sigma greater than zero are not really acceptable. Even let us say that poles with sigma equal to zero are, let's avoid them. These are the pole locations that we want, and we will want to design a control so that somehow let's try to have the poles migrate, zeros need not migrate, the poles migrate towards the left hand side. Okay, so what we want is pole on the right hand side is unstable, not desired, so we want to have pole on left hand side only. If they are not originally in the left hand side, let's do something to bring them to the left hand side. Okay, but before that, all this jargon, we really don't know how the location of poles is physically affecting, or is affecting how the system behaves. Okay, what I say is that I want a system to decay in this time. So let us say I want the system, any error that is there, that should go to below say 2% within 2 seconds. I make the specification, but where should the pole be? I should be able to match this response or better this response, the desired response, with an appropriate pole location. Okay, what we have seen is that the transfer function can be split as a sum of first order transfer function and second order transfer functions. And so because of the linearity property that you find in LTI systems, okay, or linear systems, what you can say is that you can individually analyze a first order system and a second order system thoroughly, and from that make conclusions of relating how your system is behaving with how you want to behave. I can sort of translate these specifications to the pole location. So specs to pole locations can be done if I analyze your the first order system and the second order system. So let's first go into the first order system, and let's first see the step response of first order system. Why the step response? That is because usually the simplest uh, uh, requirement that you have is that, let us say your manipulator, the joint angle Q is some Q0. I want the joint angle to go to Q is equal to Q1. So this is the specification. So the specification when I draw, so let us say Q desired, if I try to draw it, I'll say Q desired is Q1. So it at some point of time I suddenly say that the Q desired is Q1. So this response looks like a step that changes from Q0 to Q1 at some arbitrary time. We are not really interested in the time now. But this shape of the response is that of shape of the specification is that of a step. So what we want to see is that if I give a specification of a step to a first order system, how will that system behave? Okay, and can I translate that behavior of the system or some parameters in that behavior to what was the pole location of the system? So we know that the Laplace transform of a step input signal is 1 by s, and if you put it, you would get that the output will be of this type, 1 minus e raised to minus t by tau, and we can already see that the rate of the decay e raised to this is related to 1 by tau. So the greater 1 by tau is, the faster the decay. Okay, so 1 by tau, as 1 by tau increases, rate increases. Okay, so the as 1 by 2 increases, it will become faster and faster response. Okay, so say that this tau is a time constant of the system, and generally if I have a response like this, e raised to minus t by tau, then at the time t equal to tau, you will reach the 63% mark, or 1 minus e raised to minus 1 times the final value that you want to reach. Okay. And typically at 5 times the tau, 5 times the time constant, you will reach so close to the steady state value such that it doesn't really matter. You can say that the system has settled. But if you actually see that when it reaches the value 1, you will see that C of t is 1 only as t tends to infinity. But that is again something that impractical. You can't wait for infinite time. What you need is that you need to stop some time and say that it's practically, so the stopping time, the time that you consider the system to have actually settled, is 5 times the time response. Now if I say that, as I said earlier, if I say that I want to settle within 2 seconds, which would mean that I want 5 times tau to be less than 2 seconds. So which would give me a limit of the time response. So t should be less than, say, 0.4 seconds. Okay, and depending upon that, now I can try to design a system, or try to modify the system in a manner such that after the application of the control in that final system, the time response or the time constant is less than 0.4 seconds. If I had a specification of settling time to be 2 seconds. Now let's go to the second order system, the more complicated of that. Okay, so in a typical second order system, okay, with a steady state gain of 1, you have this structure in that system. Here this omega n is called as the natural frequency of the system, and it is the frequency at which the system will oscillate if there were no dissipating or dampening terms. So if you go back and see the case of a mass being connected as a spring alone, okay, this mass will oscillate at some frequency. That frequency is called as the natural frequency, and to that if you add a dampener, you would have it will still oscillate some frequency at some frequency, but now what would happen is that the amplitude of oscillation will decrease, but the frequency at which it was oscillating without this damper is omega n. Okay, and the frequency at which it will oscillate after the damping is called as the damped natural frequency, omega d, and the amount of damping that is added by this dampener is called as is characterized with this damping coefficient xi. Okay, that's why this is called as the damping coefficient or damping constant. Now, when you have a system in which the damping was 0, that is, it kept on oscillating, that was called as a undamped system, that is zeta equal to 0 or xi equal to 0 is called as an undamped system. Okay, but you don't want undamped system because they are not going to settle anywhere. They are going to simply oscillate forever. So you are not interested in this sort of systems. and you can have the zeta to be less than 1, in which case the response, the system is called as an underdamped system. Zeta equal to 1 is called as a critically damped system, and zeta greater than 1 is called as an overdamped system. But overdamped system, actually, with zeta greater than 1, if you try to write this equation, try to solve the roots of this equation, you will get as minus 2 zeta plus or zeta omega n plus minus root of 4 zeta square omega n square minus 4 omega n square. But if zeta is greater than 0, this will come out to be a real root. So I'll get two real roots. I can actually write this as something s minus a times s minus b, this equation, which would mean that I can decompose this into two first order systems again. So an overdamped system where zeta is greater than 1 is actually two first order systems coupled together. So it's something that is theoretically a second order, but not really. Practically, you don't even consider them to be first second order system. Okay. So now let us see the step response for a second order system. Okay. First of all, let's see the underdamped response. So in the case of an underdamped response, we know that this factor xi is between 0 and 1. So I can write it. I can write this. Yeah. So I can write this in this manner. Okay. Zeta omega n square into 1 minus zeta square omega n square. So I can, and this can be written as omega d. Okay. Where omega d is a damped natural frequency. Okay. So this is s plus zeta omega n the whole square, and this is omega d square. So if I try to write the inverse Laplace transform for this expression, this 1 by s becomes 1, and this expression s plus zeta omega n by this one, and this these two components will turn it to a sine and cosine terms. Okay, and if I say that if I define an angle phi, a constant phi, as the tan inverse of root of 1 minus the damping coefficient square by the damping coefficient, I can sort of simplify this earlier equation into an equation with one term, which is a delayed sinusoidal term and a damped sinusoidal term, something like this. Okay, so it starts from 0 and it oscillates, and the amount of oscillations decreases. The rate at which the oscillation, the magnitude of oscillation decreases, actually depends upon this factor zeta, and the rate of oscillation, the frequency of oscillation is actually this omega d, depending upon the damped natural frequency omega d. Okay, now there are few things here that we want to see. What we want in general, what we want to do is that we want the system to settle as quickly as possible. Okay, so one thing is a factor that we want to see is the settling time, that is Ts. Okay, and the other factor is I want to get to the final desired position, let us say 1, as quickly as possible. So that time when it first reaches this is called as a rise time. Okay, and you see that because of the oscillations, it can happen that the response goes above 1, and the maximum overshoot that happens unimaginatively is called as MP, the maximum overshoot. Okay, or peak overshoot, which the maximum is the peak time, or TP. Okay, so and there is one more factor, that is the delay term, the delay time. There may be some inherent delays in the system which we have not actually looked into earlier. So that may cause some delay in the response, and that is captured by the delay term, which is considered the time taken to reach 50% of the steady state value. The rise time, as I said earlier, is time taken to reach the steady state value for the first instance, and solving for solving C of t by putting C of t equal to 1, you get the rise time to be this expression. Okay, the maximum overshoot or peak overshoot and the peak time are respectively the maximum peak value measured from unity, okay, and the time at which the peak occurs. So the peak can be discerned by setting the derivative of c by dc by dt, the derivative dc by dt to be 0 at this point, okay, and you will get the peak time. You can find the peak time to be pi by omega d, okay, and from the just substituting the peak time into the equation of c of t will give you the maximum overshoot. Okay, so one thing is that yeah, so maximum overshoot, but I think there is something mistake here. Do you see the mistake here? Yeah, there should be a negative here. Okay. So there is one thing. You see that let us see what happens to the peak time. If I want the peak time to be small, okay, if I want the peak time to be small, what should I prefer? Zeta to be large or zeta to be small? Can you help me out with that? Hello? Let us say as zeta increases, what would happen here is that the denominator decreases. So as zeta becomes close to 1, the peak time becomes larger. So I want the damping ratio to be small if I want a quick peak time, if I want the peak to be quicker. Okay. However, if the damping ratio decreases, this increases. So MP increases as zeta decreases. Okay. And TP increases as zeta increases. But I want both of them to be less. I don't want too much of overshoot happening. I don't want the response to be slow. So this is something where a compromise has to be got. So we have to find an optimal value of the damping ratio, even the desired damping ratio, so that both of these conflicting objectives can sort of be compromised. Okay. The next thing is the settling time, which is sort of, if you go back, you have this thing. After some time, what would happen is that the entire response is within certain band around my final value, the steady state value. So I want to find that time after which the final value or after which the value of my function is within certain tolerance level of the steady state value. Okay, so as a thumb rule, if you have if you want this a 2% steady state error, so what you have as a settling time is minus the natural log of 0.02 divided by zeta omega. If it is 5%, this will become 0.05. So that is the thumb rule. And generally 2% error is taken, so this will come out to be approximately 4 by zeta omega again, so as the settling time. Again, now as zeta increases, the settling time is going to what? Will it decrease or will it increase? So as zeta increases, the settling time is decreasing now. Okay, for underdamped systems. Okay, so as zeta increases, the settling time decreases. That is good. So zeta increases, TS decreases, zeta increases, MP decreases, zeta increases, rise time increases. Okay, so this is something. So zeta being increasing is good for settling time. It is good for reducing the peak overshoot, but it is not good for the rise time. Okay, so again something now they are not reconciling good well enough. So we have to find something, some optimal value of zeta such that everything can be done. Okay, as I said, that overtime system are actually sum of two first order systems. So let's not go into that also. That's useless. So and critically damped system are exactly the systems where the damping ratio is equal to 1. So the damped natural frequency doesn't exist. Omega n root of 1 minus xi square is equal to 0. Okay, and you can get the response for the um underdamped system and set zeta equal to 1. Okay, there is something wrong here that I had written. This zeta should not be there. It gets cancelled out. Okay. So what you have here is, if you observe these two parts, sine of this is some sine at by a, as at tends to 0. When you have if you make zeta tend to 1, or the damping ratio tend to 1, okay, you will have you concentrate on these two terms. This term of 1 minus xi square will get cancelled with itself, and this term will become omega, will just become so there will be a zeta, this will just become t. Okay, so I'll have omega and t coming in here. Okay, and I would see that at this point of time, when you have a critically damped response, okay, I have an extra omega and t coming in the response, and this extra omega and t is going to speed up the response. As t increases, its strength increases, so the omega and t is going to speed up the response, okay, as compared to an overdamped system. And the omega d, the damped natural frequency, is going to 0, so the oscillations are going to disappear when you compare to the underdamped system. So critically damped system is theoretically the best sort of damping that you can settle on. So when you have a robotic manipulator, you will try to get a damping that is close to critically damping, because you don't want your manipulator to oscillate at all. Okay, so I don't want the manipulator to, I want the manipulator to make smooth motion from one place to another. So I don't want it to go like this and do this. So this sort of oscillations is not necessary, it's not needed for it. Okay, so you don't want that to happen, and because of that we go for the critically damped system. Okay, so the observation that you have here is that when you have a first order system, you don't have any overshoot, okay, but it is very sluggish. So, and when you have a second order system, you have oscillations coming in, a feature that was not present in the first order system. And the underdamped system have a fast response, but also come up with the problem of having oscillations. The critically damped system have fast response, but no oscillations. Okay, but they are quite difficult to achieve. So you say that my target is having a critically damped response, but practically I accept, I would have to accept that I can't get perfect critically damping. I can try to tune the parameters so that I get as close to the critically damped as possible. So that will be the aim that we want to achieve. So that comes the end of this particular lecture. We will try to use these concepts to design different controllers from the next lecture. So if you have any questions,